So random forest is an extension of a decision tree. It's an ensemble learning algorithm. In other words, it uses many decision trees to make prediction. Let's understand this through an example. Suppose I have 4 decision trees. 1, 2, 3, 4. So the first decision tree makes a prediction of an apple. The second decision tree predicts an apple. The third one predicts not an apple. And the fourth one predicts an apple. In this case, majority is an apple. So your random forest is going to make a prediction that the data is an apple. So it's like asking 100 expert instead of just trusting one expert. A random forest algorithm, by the way, can be used for both classification and regression. If you recall, regression refers to when you're predicting a numerical value, and classification when you're trying to predict a categorical value. So it can be used for both the cases. Now the algorithm for random forest. Step 1. You create random samples of data and features. So from your data set, suppose it has total k records, you repeatedly select n random data points with replacement. And this is called bootstrap sample. This process is called bootstrapping. And also, from this data set, you select m random features out of all the available features. So each one of these samples and each feature, they will be used to build one decision tree. Let's understand this through an example. So I have this data set right here. In this case, I have total 6 records. My k equal to 6 because it has total 6 records. And I select 3 samples from this. My first sample is this, my second sample, and my third sample. So my first sample I'm selecting, I have only 4 points, n equal to 4. So these are my samples, id equal to 2, 4, 6, 2. In other words, I'm selecting this one, I selected number 4, which is this one, and I selected 6, and I also selected 2 again twice because this is done with replacement. If you recall, I explained this was done with replacement. Okay, and then in this case, in this sample, I don't use all the features. I only use a small set of features. In this case, I'm using only 3 features. My m equal to 3, that would be this step right here. So in this case, I'm using only feature x2, x3, x3, sorry, x2, x3, x4 for sample 1. For sample 2, my size is same, size is 4. And in this case, I'm using this ID one, first one, fifth one, third one, and fifth one. That would be this one, fifth, that would be this one, and 3, that would be this one, and fifth, that would be this one right here. And I'm choosing fifth 2 times. And in this case, my feature would be x1, x3, and x4. So these columns are my feature in this case. For my third sample, in this case, my size is 4 again. In this case, I'm choosing 2, 1, 4, 3. These are my rows. So 2 would be this right here. 1 would be this. And 4, that would be this. And 3, that would be right here, this one. So I'm selecting these records right here. Then out of these among these 4 records, I'm selecting only 3 features. My features are x1, x2, and x3. So I'm going to be working only with these 3 features. Step 2, now you build a decision tree from each sample. So each bootstrap sample that we got it from previous step, we grow a decision tree. So at every split, what we are doing, we are selecting a subset of features at every split. This is how we are splitting our node. So in this case, let's say this gives me this decision tree. This particular sample, let's say it gives me this decision tree, and this sample, suppose it gave me this decision tree. Now in this particular decision tree, I only used these features, x2, x3, x4, because only these features were present. And in this particular case, I'm using only feature x1, x3, x4 because only these features were present. And same thing with your sample 3. In this case, I'm using x1, x2, and x3 because only these 3 features are present. Step 3. Now you generate predictions from all trees. So if you're working with a classification task, this is going to generate maybe some type of class. Maybe let's say this generates an apple. This one could generate an apple. And let's say this generates not an apple. That's the class it generated. If you're working with regression task, this is going to predict a number. Let's say this predicts a number 2, this predicts a number 3, and this could predict a number 4. Now comes to step 4. In this case, you combine all the predictions to form the final output. So for the classification, it predicted an apple, this predicted an apple, and this predicted and not an apple. So in the classification case, the majority is an apple. So your output is going to be an apple. So your random forest is going to make a prediction that it is an apple. On the other hand, if you're working with regression, and let's say this number was 2, this number was 3, and let's say this tree predicted number 4, then the average is going to be 2 plus 3 plus 4 divided by 3, and that's your answer. That's your numerical answer for predicted by your random forest. A side note, the bootstrapping process that we performed in step 1 and the aggregation that we are performing in step 4, which is this step, is commonly referred to as bagging. Now, this is done to reduce variance. So in the random forest, why is it called random? Well, that's because we are selecting random samples and random features. So here we selected 3 samples, this one, and this one. In this first sample, we randomly selected 4 records. This, and this. In the third sample, we selected 4 records that were random with replacement. And same thing with your features. We randomly selected 3 features. Over here, I selected X2, X3, and X4. Here, I selected X1, X3, X4, and here I selected X1, X2, X3. So because I'm selecting random samples and random feature, that's why it's called random. So why do we use bootstrapping? In other words, why do we do random sampling of data? Well, there are 2 main reasons. Number 1 is to reduce overfitting. The second one is to provide you built-in model validation. Let's understand the first one. Now, if every single tree is trained on the same data set, then all these trees, they are going to look similar. And this is going to overfit your training data. If you have different data, that will produce different splits, and each different split gives rise to different trees. So bootstrapping, it ensures that every tree it sees a slightly different data set, so that each tree it learns something different. In other words, each tree learns something new. Now, bootstrapping, it also provides you a built-in model validation. So since some of the data sets are not selected, we only selected few of them. For example, in this case, we selected 2, 4, 6, 2 twice, and the other data points were not selected. The one with the ID 1, ID 3, and ID 5, these were not selected. Because these data sets were not selected, your bootstrapping can use this as your separate test set. So this kind of helps you estimate accuracy without creating a separate test set. So why do we perform this random feature selection at each split? Well, one of the reasons is that to break feature dominance. If you have one strong feature, if it exists, then all the trees, they will use this at the top split. And this would make all the trees very similar. In order to avoid that, we do random feature selection. So this actually forces the trees to explore different feature combination. This way it increases the variety in your trees. Now, the other reason is to reduce correlation among different decision trees. So for your strong ensemble, your model, it must be accurate individually, and also each model, they should be uncorrelated with each other. Now, random feature selection, it reduces correlation. It gives you better combined prediction. And finally, it improves generalization. So if you have trees that are trained on different feature subsets, they will capture different data pattern, they will avoid overfitting, and also they will perform better on unseen data. So how many features should we select? The researchers, they have found that taking a square root or log of the total number of features, it works pretty well. So if you have, let's say, 9 features, then you should have approximately under root 9, that will be 3. So you should take 3 features in each sample. Or you can take log. You can take log of 9, and whatever the answer is, you can take that number. So to recap, the combination of both random sampling of data and random feature selection at each split, this creates many diverse and uncorrelated trees. Also, it reduces overfitting and improves accuracy and stability. Now let's look at some of the parameters in random forest. Well, one of them is a number of estimators. This actually calculates the number of trees that you want in your forest. The more trees you have, it will lead to better performance, but it comes at the cost of computational time. Start with a value of 100 and increase as needed. And then there is a maximum depth. So this captures the maximum depth of each tree. Now, the deeper your trees are, the more complex pattern it can capture. But also, it runs at a risk of overfitting. So, generally, it's a good idea to experiment values between 5 and 15 and consider lower values for smaller data set. And then there is maximum features. This is actually the number of features that is considered for splitting at each node. A common value is square root of the total number of features. You can adjust this based on your dataset size and your feature importance. Criterion. Now, this is a function. It is used to measure the split quality. Well, this could be either Gini or entropy. Gini entropy generally is preferred because it's slightly faster, but both generally they kind of give you similar in performance. Minimum sample split. This is the minimum number of samples that is required to split a node. Higher values that would prevent your overfitting, but if you have too high, that will make your model complex. So it's a good idea to start with 2 and adjust as needed. And then there is minimum samples leaf. This one is the minimum samples that is required to be present at a leaf node. It is similar to your minimum sample split, which is right here from this step, but it's focused mainly on the leaf node. So it's a good idea to start with 1 and adjust as needed.